What if I said to you, I want to store 31 numbers in an array, and those numbers are going to be anywhere from 0 to 999, and I want to be able to search to see if they exist as fast as possible. Okay, so we're going to take a look at a way to store these numbers that's going to work out to be efficient. So if I start thinking of some numbers, I'm just making numbers up here, folks. 111, 111, 997, 1, 0, 999, 112. Okay, so I had some numbers going on here, and I'm saying, okay, so if I want to be able to search to see if they exist as fast as possible, I'm going to store them in an array of size 0 to 999. So I have the first 6 of the 31 numbers. And I'm going to say, okay, 111. I'm going to store it in 111. So if I said to you, does it exist? You would go to the array, go right to location 111 and say, yes, it does. It's there. If I said the number 2, does it exist? You would go there and say, nope, it doesn't exist. That wasn't one of the numbers. If I kept storing numbers, I store 997. Great. I store 1. Out here is 444. That one's empty. Here's 667. That one's empty. I could keep storing the numbers in my list. 0. Yes, it's in there. 999. It's in there. 112. And if I wanted to find out if it's in the list or not, bam, that's that one-to-oneness. My big O time would be fast. Oh, the old big O time, right? It would be fast because I could find out right away if it exists or not. That would be big O sub 1. Sound good? Some of you don't know what big O is yet, right? If I went through linearly, I started here and went through one by one, searching to see if a number exists. Worst case scenario is I'd have to go all the way out to the end. That's big O sub n. Then we also did the binary one. And if you were into your big O's by now, you would know it would be log base 2 of n. So hopefully you're starting to move along with big O. I may have to change some of the groups up. I'll let you know for sure in the next couple of days. Okay, so that's great. My search time is big O sub 1. Boom. What's the problem with this? Well, if I only have 31 numbers, right, for 31 days, if I only have 31 numbers, what's going on here in my array? I'm wasting a whole lot
of space.
Yeah, I'm wasting a whole lot of space. In fact, I'm wasting about 70% of the space is going wasted. Okay, so I'm back to this, a fast way to search. This is fast, but it wastes a lot of space, wastes a lot of memory. It's just not good. Yeah, okay, well, what if I do this? I know I want to store 31 numbers in the range from 0 to 999. And here I used 1,000 spaces. It was fast search, but I wasted memory. What if, knowing I only want to store 31 numbers, I create an array of size 31? It's actually 32 there, but don't count. We'll just X this bad boy out. We'll X him out. Okay, so now if I want to store numbers, I'm looking at the numbers above going, well, I'm not going to have that one-to-oneness. It's not going to store very nice. True that. Okay. This is location 0, 1, 2, 3, 4. This is 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 25. 26, 27, 28, 29, 30, 31. I just need it for a reference. Okay. So now I'm saying I don't want to use all this memory. I'm going to cut it way back to this amount of memory, and I'm going to see, oh boy, I need to figure out a way to store these numbers in here so that I can search for the numbers faster than what I did with the linear. You know, linearly, if I wanted to see if a number was in an array, I'd have to go through all the numbers. Or if the array was sorted and I used binary, I kept cutting it in half. Can I find a way to search that's quicker than that? And the answer is yes. And what we're going to use is something called a hash function. Okay, so there's 31 for a reason. And 31, one of the good things about it is 31 is an odd number. We're going to keep that into play. Okay, I want to be able to store these numbers. Where would you like me to put 111? Any thoughts from your end? Yeah, and I wasn't expecting any, to be honest. So I'm going to have a function here, f of x, where this, I'm going to apply this function to a number like 111, and that's going to tell me where I want to store it. Because when it comes time to go see if it's there, I apply the function, and I'm going to be able to get there to check out real quick if it's there or not. The function is going to be x mod 31. Okay, so if I start thinking about it, my remainders, da 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 da. Alrighty, not so bad. So if I took the number 111 and I did a modulus 31, where would you like me to stick it? Where are my math people? They say you don't need math for computer science. Where are my math people? Thirty-one, 31, 31 is 93. 7 more gets me to 100. So 7 plus 11 more, 18. So I'm going to store this in 18. 111. So then when it comes time to search for it, boom, I'm going to apply the function and go right to 111. What about 997? 997. 31 goes in 3, that's 93. That leaves me with 67. 2 more is 62. That leaves me with a 5. Don't be afraid to tell me if I'm wrong. So 997 is going to be stored in location 5. Well, this is great, because if I have 31 numbers, oh yeah, I'm going to run into some trouble here, aren't I? My next number is 1. 1 mod 31 is 1. That's an easy one. 0 mod 31 is 0. Well, that's kind of nice as well. Oh boy, what if, okay, here's a number for you. Instead of following our list up there, I'm going to switch it up. 36, nice. What is 36 mod 31?
0.
No. Goes in once with a remainder of
5.
5. Good. So I'm going to store 36 up at 5. Uh-oh, George. Row. I have a collision. A collision. Now I have to figure out how to handle a collision. Okay. I want 5. I want it to go in 997. And I have a collision. How do I handle it? Well, one way to handle it is something called a linear probe. And a linear probe says, okay, that spot's filled. Where could I go to put the 5? Well, I'm going to move linearly, and I'm going to do to the right. So something's already there. 5. Boom. You took my spot. It's okay. What if my next number was 67? Where would I stick 67? 31
Also,
times 2.
also in 5.
Also in 5, right? So I go up, 5's filled. I move to the right, it's filled. I move to the right, it's empty. So I'm going to stick 67 in there. Now, we need to talk about this being an array of numbers. How did I know it was empty? Well, what's in there to start? Like when I create this array, it's an array of integers. What might my default be?
No,
Mm, I don't know that it's going to be null. These aren't pointers. These are just integer values. What will get started at that integer
maybe
value?
zeros.
Yeah, I'm thinking zeros. But what's the problem? 0 is one of my numbers. So I need a way to figure out if it's empty. Well, I'm taking a look at the numbers I have from 0 to 9. What might I do to start? Fill it with something else. What's something else that I could fill this with? It rhymes with negative un.
-1.
Negative 1. So what if I went through and said, okay, first thing I'm going to do is fill everything with -1. So that, note, -1 means empty. Okay, and I would go through and fill everything with -1, -1, -1, -1, -1. Good. I'm not filling them all in. You got the idea. Fantastic. So this is all good so far. I have 31 numbers, which means what's going to happen to this array? It's going to end up getting filled. Okay, it's going to get filled. Now, what's the problem here? Well, the problem is because of collisions, I keep moving to the right and I keep filling things in. And what happens if the first 30 of these are filled in? The first 30 of them are filled in. And finally, I get the number 0. And I go to put 0 in. And what do? Well, that one was full from something else. Linear probing. I keep moving across, all the way to the end. Now I end up with that linear search where worst case scenario is I have to go through this whole kit and caboodle. Well, we don't want that. So they've done studies, and it's in the book, it mentions it. According to imperial studies, if you want to store 31 numbers, you don't use an array of size 31. You definitely don't use an array of size 1000, but you use an array that is 1.5 to 2 times the size of the numbers you want to input. So for our example with 31 numbers, we'd like to use something between 46 and 62. So for us, we have 31 numbers. According to this, our array size should be, and what did I just say? Like 46 to 62, somewhere along those lines. Why? When we have these collisions, we're going to find out that we're going to have blanks to work with. So the worst case scenario isn't me searching through everything. So if I want to pick an appropriate array size to store 31 numbers, what array size would you like to use? Pick one between 46 and 62. Anybody pick one? I'm going to say yes or no.
62.
No. Guess again.
46.
No. Guess again.
56.
Nope. Nope. Don't like 56. Guess again.
50.
Nope. Don't like 50. Matthew's got it.
So probably a prime number then.
Yeah, because I just circled the whole, we're going to use a hash function that's a prime number. Okay, so if we're storing it in 46 to 62, and I want to have a hash function, because if I used 46, start thinking about some of my remainders, and yeah, to be able to use my hash function, it's not gonna be so pretty.
51.
Yeah, ooh, is that a prime? 5 plus 1 is
Uh,
6, that's divisible by 3.
61.
61, okay, that would be 1. Yeah, mod 61 might work. I like that. Mod 53, mod 47. You know, you start thinking about numbers along those lines. I think I would go with probably the 53. So in order to store these numbers, 31 numbers, I would create an array of size 53, and I would use this as my hash function. Why? We'll still have collisions, but when I start doing linear probing, I know I'm going to have 22 extra spots in there that's going to help me keep my search time down. Give us more, give us more. I will. I will. So we have insert. We inserted numbers. Now I'd like to talk about delete. Ding, 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 ding. Guess what the first number is I would like to delete? Remember, I have insert. I can fill it up. I can say search. Is 10 in there? Boom. Nope. 10's not there. It's empty. I know that. Is 5 there? Uh-oh, wait. That's filled, but I'm going to linear probe until I either find 5 or until I find a -1. Okay, till I find 5 or -1. Oh, I found it. Good. What about 36? Well, that comes here. Nope, it's filled. Nope, it's filled. Nope, it's filled. Oh, I didn't find it. So there's that whole while loop if I was writing the code to see if it's there and I find it, or I hit -1. Okay, so I want to delete. The first number I'd like to delete is 997, which means I go up to this spot and say, okay, I found it. I applied the hash function. I went to 5. Whoop, there it is. I said, whoop, and I want to get rid of it. I'm deleting it out of the array. Cross it off. I need to put something in there. What do I need to put in?
-1.
-1. Good. Good. I like what Peter's saying, because now I'm going to say, hey, okay, I just did a delete of 9. I need to do a search for 67. Is 67 in there? Well, what's 67 mod? Well, that's 5. I go to 5 and go, uh-oh, it's empty. Crap. Because if it's -1, that means I'm done. So we have a problem.
Something else.
Yeah. The afterworld, a world of never-ending happiness. You can always see the sun. Instead of putting -1 in here, what could I put in there?
-2.
Excellent. I could change this and make it -2. That way, when I go to search for 67, I go, uh-oh, it's not there. This guy is empty. So either a -1 or a -2 means it's empty. But that, because it's a -2, I'm going to do a linear probe to search to see if the number's in there. So now if I do a search for 67, it's not -1, move on. It's not 67 or -1, move on. It's 67, I'm done. So we've now come up with a way to handle insert. If I delete something, I need to put this -2 in. What if I now said, I'd like to insert, let's see what we got, 98. Where would 98 go? So is this tough math, or it's more you just don't feel like answering questions? more you don't feel like answering questions.
Go
Yeah.
in, it would go in 5.
Yeah, it would go in 5. So, or yeah, mod 31, it would go in 5. And I say, ooh, it's empty because it's a -1 or -2. So even though we started out simple, we have to make sure now that we're doing this, I check to see if a -2 is there as well. All right, good. Good, good, good. Okay, everybody has the idea of what's going on here, right? We all like it? All right, so let's do another one just to make sure we have it. I want to store 8 numbers. That's not too bad. I want to store 8 numbers. So the first thing I need to do is decide what's my array size.
Eight.
Now,
12 to 16,
12 to
right?
16, and what would you like it to be?
Can we go, isn't 13 a prime number?
I think I like 13. So now I'm going to create an array of size 13. Let's see, that's 2, that's 4, right? That's 5, 6, 7, 8, 9, 10, 11, 12, 13. That gives me 13 numbers. These get a little funky out here. 0, 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12 kind of deal. Excellent. Okay, so now I'm going to add some numbers. Let's see what we can come up with in this array. I'm going to add 25. Tell me where it goes. Insert 25. Where's 25 go?
1.
25. I'm modding it with 13.
Oh, 12.
12. Good. That's not so bad. 4. 4 goes in 4. That's not so bad either. How about 29? Where's 29 go?
3.
Okay with that. Where does 3 go?
13. Wait, no.
5.
5. Good. Where does 38 go?
3 mod 13.
13 doesn't go in 3, so the remainder is just 3. I try to put it here, it doesn't fit in, so I have to linear probe over 2 spots.
Okay.
38,
Would you go to 0?
yeah. Oh, uh-oh, there's another twist, right? We just threw ourselves another curveball. What happens if I get a number and I'm at the end of the array? I now have to take this whole wraparound in play. This seems so easy at first when all I was doing was inserting numbers. But now different pieces of test data is doing different. All right, if I search for 25, not too bad. It's there, right? 25, boom, it's there. Found it really quick. My search time was so short, it's unbelievable. What if I wanted to search for 38? Again, I would go to 25, and now I need to not only in my insert think about the wrapping around, also in my search, I have to think about the wrapping around. What about 3? Yeah, we know we'd go to 3. It's not -1, it's not -2. So linear probe, because that's my probe sequence, says go to the right. Go to the right. Just like when I got here, I had to go to the right and it wrapped around. All right. Delete. Let's pick a number to delete. 29. What did we say we're going to put in there?
-2.
-2.
-2. Okay, good. I think this test data is if I say delete 25, what are we putting in?
Negative
Yeah,
2.
again, that's another -2. And if I do a search again, if I search for 3, I go to 3, it's not there. It's empty, but there was something there at one time. So that means do the probe. Probe to the right, 4, probe to the right. Oop, I found it. Again, the rest of these empty ones, we'd have -1s in there to start. Again, same with the search. I'd go and land out here and get the -2, and then I'd wrap around, kind of idea. So plenty of good test data and everything to see what's going on. Okay, so some notes. What if I would love to improve performance? Okay, I have this section here. I want to improve performance. Well, we've already, this looks like a really good test question. Okay, this looks like a good test question. One way to improve the performance was we changed this size to 1.5 to 2 times. We increased it. Instead of 31, we went to 53. That way we wouldn't have as many collisions. We'd have some empty spots to work with, but we also weren't wasting a lot of memory. Again, we said 1.5 to 2 times the size, and we'd love it to be a prime number. Second strategy is collisions. Well, we've done collisions, and what we did was we did a linear probe, moving to the right one at a time. Okay, but we're going to get, so that could be a primary, this is primary. Other ways to handle collisions would be maybe quadratic probing instead of linear. So let's see, we're going to go, I is 0. So we'd go 1 to the right, maybe then go 1 to the left. Then maybe go 4 to the right and 4 to the left. Instead of going right 1, right 1, right 1, right 1, this is called quadratic probing, where it goes and moves left 1, right 1, left 4, right 4. A different way to look, and then to get maybe possibly get more spread out than the linear, which is going side by side. Okay, it's a way of possibly separating it. All right, and we have something called double hashing, where we could have several different ones if we want. Just some ideas of going on. The third way is to use a different hash function to improve performance. And as you see down here, we have our hash function, which takes it and puts it right in the spot. What if I was dealing with letters? And you think about letters, okay, so there's 26 different letters because I want to store names. Alvin is A, I'd store him in 0 kind of thing. So I have all this going on with my letters, but there aren't going to be many Q's. There aren't going to be many Z's kind of deal. So what if I, instead of just taking them straight up, I might average the first and last letter. Like if it's a person's name, Brady Wan, I take the B and the W and their numerical values and average them together to try and move around. So look for different types of hash functions. Okay. So you see what we have going on here. 3 ways to improve performance. Table size. How do you handle collisions? Use a different type of hash function kind of deal. All right. That was a good 30 minutes. So what do I have now? Write a program to demonstrate what we've talked about up to this point. Insert, delete, search, and traverse. Well, we're going to do this with just arrays, and I'm going to put you into groups, and this could be one of those divide and conquer type of deals. We have 14. So I think I might just make 2 groups of 7. We've talked about inserting. If something's there, you can just do a linear probe to the right. Okay. Delete. I have to take that and put a -2 in if something was deleted. Search. traverse. So that whole -2 is going to come into play. So let's come up with what I want you to do. We're going to be putting in numbers. How many numbers would we like to put into our array?
10.
10? Okay. So if we're going to be putting in about 10 numbers, we should have an array size of what?
What, 15 to 20?
15 to 20. Give me a nice number in there.
17.
Yeah. So I think we're going to use 17 so we can use the hash function of mod 17. So our array, wait. Our array size is, we have 10 numbers, 15 to 20. We have an array size of 17. Okay. We're going to store 10 numbers. What's the range of those numbers? So 0 to 100, 0 to 99.
Mm-hmm.
Okay. And then, what are you going to test? Well, you're going to do your insert and you're going to test putting numbers so that they bump each other. And then the wraparound. So with insert, we want to have collisions and we want to insert. So I have collisions and I have to wrap around. Delete. I want to delete something that may already have a couple of numbers in it. Delete that first one in the front. Make sure it becomes -2 and then try to insert something in that spot. So when you're coming up with test data, we have an array of size 17. And I'm starting to think of some numbers that I'd like to put in. So what if this is 3? So 3 would be a number, 20 would be a number, because that would go to location 3, and then 20 would have to go to 4. 37 would be a number. So I would put that in because that would have to go to location 5. I might put in insert 16 because that's going to go here. What would I need? Maybe 33, because if 16's going at the end, where would 33 have to go?
0.
Yeah, it's going to have to wrap around. So you see what I'm doing with test data here. So the person that's writing the demo in your group, you might be stealing these numbers from me real quick. And then what are we going to do after we insert all these? Well, delete a 3, so that this becomes, oh, what else might we need in here? We're going to need an insert, a delete, a search, and this says traverse, but what do I want instead of traverse?
Linear probe.
How about just a print?
Oh, okay.
A print, okay? So an insert, a delete, a search, a print, and a demo kind of program. Got it? I will stop the recording now.